Welcome to Happy Path Programming. I'm Bruce Eckel.
I'm James Ward. All right. Well, today we just have Bruce and I just hanging out.
Yeah, I just got back from the Strange Loop conference, which I'd never been to, or
I've never been. I always felt that Strange Loop was where the cool kids hung out, and I wasn't cool enough.
No, I wouldn't say that. It's just, I think what you're seeing is a survivorship bias because there are some really interesting presentations that show up on YouTube, and you see those and you go, oh, they're all like that.
Yeah.
And it's not that, there aren't lots of good presentations, but they aren't like all at the level of the ones that have filtered their way through YouTube.
Yeah.
So, but I got
a wider range than I have.
There is a
assumed.
wider range. Yeah. And because I had the same impression. Yeah. And that's a lot of what motivated me to work as hard as I did on this presentation. So ultimately the illusion was good, but I mean, it's an interesting take on conferences, but not as different as one might expect.
Yeah.
So
maybe I have to try to go to the last one next year.
So. Yeah, because the guy who has been organizing it for next year will be 15 years.
Yeah.
He's tired.
Yeah.
Which I totally understand because he's like the focus. Everything. Yeah.
He's the center.
Yeah.
I organized a conference once and I don't really want to do it again. It's a lot of work.
Well, when you do it that way, yeah. If you make it, a self-organizing conference, it's not very hard. Like what we do at the Winter Tech Forum is actually pretty easy, and you're not stressed out all the time.
So. Should we do a Winter Tech Forum this year?
I would like to. Winter? It all depends on the
COVID climate.
Well,
companies paying for people to travel for.
Turns out that is the critical factor because there's every once in a while there's someone who goes, I will pay for myself to come to this, but it's significant, and
most of the time companies are paying,
right, and providing time. I mean,
you don't have to take vacation.
Travel. Yeah, you're not taking vacation because it's an educational thing, and I wonder how many companies have said, wow, it's awesome, like during COVID when we haven't had these education expenses. How long can we stretch this out? Until people start going, I'm not growing as much as I.
Well, maybe we should ask our listeners that let us know if you'd be interested in doing a Winter Tech Forum in Crested Butte, Colorado.
Yeah.
And usually we did it somewhere in the February-March range. Is that right?
Yeah, generally, because February is when it starts to warm up a little. January is when it's typically
cold and snowy,
really cold. And usually I've tried to schedule it in various ways, but usually now I've just decided, because on Friday night we have the yurt dinner.
Oh.
And so I try and figure out, is there a full moon Friday night?
So we've got a lunar-based calendar for
the decision-making process, because it's like whatever date you give, somebody will go, oh, that doesn't work for this reason.
If you've got to synchronize to something, synchronize to the moon.
So that when you ski back from the yurt, it's in the moonlight, which is wonderful.
Which is very delightful.
Oh, it's great.
Well, the other alternative is to go on a new moon night, because then the stars are better.
Stars are good. Yeah, that's true. Yeah. That's the fallback position. So
we're lucky in that we get to do this many times in the winter. At least I do.
So my hope is that it works. But I think I need to get more concrete feedback to know whether it's time or if we have to wait another year before we can do it again.
Yeah. So if we are sent, I don't know, a Bitcoin per person and before the end of the year or something, then we'll set the date and do it. How do we get people to commit? What do you call those accounts where you put something of value?
Escrow.
Yeah. You need
or just an early, the common thing to do is an early registration discount.
Right.
So, which I'm not a huge fan of those, but
Yeah.
But okay, there are reasons to do that. So maybe we'll have to do it this time. I don't
Yeah.
know. Anyway, we'll see.
Okay. Well, let us know if
Yeah.
people are interested in coming.
Yeah,
It'll
for
be
sure.
fun. Okay. So I want to hear about Strange Loop and your presentation.
Yeah. So, this started happening a couple of years or so ago, and I think a lot of it came from our examination of our working towards better understanding of what functional programming is and why you're doing it and everything, which is it's weird at first because if you've been used to doing things in the object oriented way, which actually came in my professional lifetime. We started with procedural languages like Pascal and C, and I started in assembly language. Well, at least that was my initial. I did some work in BASIC, but then the serious work was in assembly language, and that's a whole different worldview.
Yeah.
And with assembly language, you're writing code, and we were working with embedded systems. These were test equipment, and so we had limited memory for programs.
Yeah.
And so anytime you had a duplicated code, you'd want to put that into a function. But it was really more of a subroutine. And you had to, if you were making an actual function call, you had to push your arguments on the stack yourself, and then you'd call the subroutine, and in the subroutine it had to know to pull the arguments off the stack and push the result onto the stack for the return, and then the caller had to pull. So it was all this stuff you had to do by hand.
So it's been a long time since I've done assembly, but but like you, I did Pascal and assembly, or like those were my first two languages, but I just don't remember anything about them. In assembly, is there a way to basically have something like a function, like some reusable piece of logic? Is that what you're saying?
That's like a subroutine.
Okay, so you can define a subroutine.
You can define a subroutine, but if you were passing, it was basically just a way. You could call it. It would remember the stack where it would remember the location you called from, and so you could do the call, and then at the end of the subroutine you'd do
back to where you were.
So it was a go sub and return some form of that. But if you wanted to pass arguments, you had to do all that yourself and return values. So it was really just a way to. You had duplicated code. You go, oh, well, we need to save that space, so we'll turn it into a subroutine. And then, there were other benefits like debugging in one place rather than across multiple places and things like. But it was purely, it was really driven by needing to
reduce the size, the footprint of our application.
You had this many bytes, and you needed to save it whenever you can. And people would go to all kinds of. This is. People would come up with things like self-modifying code and stuff like that to cram things into this space. It was kind of crazy and not particularly maintainable, but they did it because they had to. So
tangent on this. I remember seeing so much amazing stuff from the demo scene back in those days around assembly. Future Crew was the one that was the most astonishing. And so they would do these competitions to create the most amazing visual musical demo that they could in assembly. It was like all assembly, and they had some competitions that would constrain the size that you could have your program exist in, the size of your program. But what people would do in like a meg of assembly was just unreal. 3D ray tracers and stuff. So it was mind-boggling back in those days to see just the crazy stuff people did with assembly.
Right, and those skills that they developed were let's say contextual. And so I think part of the resistance to going to higher level languages, I mean, a lot of it was those people who had worked so hard to make things efficient. They're going, oh, well, I mean, this is so inefficient.
Yeah.
You have the C compiler, it's spewing out all this extra code that you don't need. I could write that in assembly and make it really compact. But that wasn't the problem. The problem was productivity, and memory was starting to get cheaper, and the real problem was how much it cost to develop these things, and also the inherent limitation of complexity that you could build in an assembly language. And the more the cost was exponential as it got more complex, and it was really, so it ultimately was a cost thing. And so so we had these higher level procedural languages like Pascal and C that would do the function calls for you. And so now all of a sudden we have this ability to easily do function calls, whereas before it was like, okay, well, if I'm forced, I can do that. And it was also hard to make reusable code because whoever was calling a subroutine that had arguments and return values, had to understand all of that.
There's a contract there that was not explicit.
Right. It had to be in comments, and often the person, writing the assembly code was just going, it was the beginning of it works for me. And it's like, for my application, this works. And I wasn't trying to create reusable code.
It's like, you specified, you pushed those onto the stack in the wrong order.
Right, exactly.
It's like, I didn't know what order they were supposed to be in. Your documentation was wrong.
Well, read the code, and so this was a big step forward, but now we can easily create functions, and people weren't really used to doing that. I think one of the things, I just had this insight yesterday, that most of what people were doing is what we would today call scripting. And I mean, it's almost like, the application we were working on last night. You're just taking whatever you can to put it together to get it working. You're basically writing a script. You're not trying to create reusable components other than within your application when you're forced to. And so it's like, there's a whole lot of programming like that. And so this idea that we have functions and we should partition it up into functions for some reason, because then you create reusable code. And there was all of these, descriptions around this. And
when you're in scripting mode, I sometimes will admit I just copy and paste things instead of doing the correct reusability.
You're just trying to get it to work, right? And so you're just, I think especially scripting is exploratory. You're just going, I don't even know if does this program even serve my needs? I won't know until it's working, and I go, oh no, that's not doing what I need it to do. And so you're not trying to necessarily use all the best practices. It's usually, you get it working and then you go, okay, now I'd like to go back and improve this. And I see places where, I need to allow for further expansion and things like that. So, we were moving through this. We had these procedural languages, Algol, Pascal, C, there was probably some others. And the thing is, Fortran and COBOL, one of the super early languages, they had ways to do subroutines, but it was awkward. And especially in those languages, people were strictly just trying to solve their problems. And so rather than, and they had to, when I was at Pomona College, I had a work study job in the computer center, and they had these doors, and you'd open the door and you'd put your stack of cards with rubber band, or they had to be in the right order, rubber band around them, and then close the door, and we'd open the door on the other side, take the stack and put it in the card reader. It would go down, it would, had a line printer, it would generate the results. And often, because of the backlog, it would be an overnight process.
Wow.
And it's like, so do you want to, it's like, okay, there's some functions out here that supposedly somebody else has written and they're useful. Do you want to take the risk of calling those, or just writing that code in line
Yeah.
and, you know, feeling comfortable that you're not going to get that compiler error.
Yeah.
Because if you get the compiler error, then it's another probably 24 hours before you get or some number of hours. You know, the turnaround time was terrible.
Yeah, that's a pretty bad developer experience.
Yeah, the concept of developer experience wasn't there. It was just like, the computer will do
I get
calculations
frustrated
for
if my inner developer loop doesn't have a compile time under a second, and you're talking about a compile time basically that, validation that takes 24 hours or something.
Oh yeah.
Yeah.
No. And so you would do a lot of reading of your own code to see, did I get this right before you would submit it?
Yeah.
Yeah.
Okay, so at Strange Loop, you did a presentation, and what you've just been going through was some thoughts that you've been having after the presentation, or what?
Yeah, mostly because I did the presentation, which was called Polymorphism Unbound, and it's not up on YouTube yet, but it will be in the next couple of weeks.
Yeah,
and it was my process through all this was, at the time I was entering the workforce, I guess, there was this movement called structured analysis and design. And I was just coming out of school and thinking, all right, here's this movement, and this gets us where we want to go. So I'll studied it, and I took 1 or 2 workshops and everything. And it seemed all very strange to me. But the idea of structured development, structured analysis and design, was that, okay, instead of writing these long scripts, they didn't put it this way, but in hindsight, I can see this is how we were evolving. Instead of writing these long inline scripts, we want to break things up into functions, because functions are good for reasons.
Because reasons.
Yeah. And, in hindsight, I understand, they were actually solving the business problem of, instead of having 1 or 2 or 3 people writing this program, we are writing bigger, more complex programs, and we need to have
human scale,
lots of people working on it. And so how do we partition that work?
Yeah.
The function is the perfect way to partition the work. We'll break it up into functions that one person can work on.
Yeah.
This function, and then that will solve our, it was designed to solve a management problem.
Yeah.
So that was kind of turns out sort of a distraction, because the design was not designed for better programming. It was designed for easier management.
Okay.
But it was a whole, and so it faded away, and people probably don't remember it now. Then when I was at the University of Washington, we were trying to come up with better ways for scientists to be able to use computing, and like the idea of taking an equation that you write on the board and directly translating it into code was very appealing. So operator overloading and being able to do these things with objects where you don't have to allocate storage and deallocate the storage, all that stuff that you had to do by hand and people would get wrong. So we looked at Objective-C, and then we decided to use C++. And this is early days, so there was very little in the way of documentation, and to get there was a tool called Cfront, which would take your C++ code and compile and translate it to C code. And this had to be a subset of C that was, universal, because there was no standard C at the time. And so the Cfront would generate C code, which for me was very useful, because when I came across this idea of a virtual function, I was like, what the heck is that? This is a totally new concept. And to figure that out, ultimately, I beat my head against it for a long time, but then I started looking at the output of Cfront. And so I could look at the C code. I didn't have to look at the assembly code. and I could see, oh, well, they're doing this thing called dynamic binding. They're building a table, and based on the type, it jumps to a different part of the table. So I could see eventually unravel what was going on.
Huh.
And my perspective was, wow, look at all the things you have to do to make this work. You have to have a base class, virtual functions, derived class, et cetera, et cetera. This must be really important. Probably we should be focusing on this and doing it a lot,
right,
and everything. And in hindsight, of course, that was probably not the right thing. But the point was, my perspective on what polymorphism was through this kind of narrow keyhole
okay,
of dynamic binding.
okay.
So the reason I called it, Polymorphism Unbound was, it sounds like Prometheus Unbound,
yeah,
right? Which is Shelley, I think.
okay.
Anyway, so that sounded cool, but it was really, oh, okay, there's more polymorphism than just dynamic binding. And once you start seeing this, and so what is polymorphism? Really, it is treating a group of types as a single type. And so most of the time we see that in a polymorphic function, we see that as the parameter represents more than one type. And so with polymorphism, that works if you have, pets, and you go, okay, so this thing takes pets, but that means it can take a dog or a cat or a goldfish. Those are different types treated as a single type.
Yeah.
But to do that, you have to squeeze those into this type hierarchy. And then
so that's the inheritance model of polymorphism.
Yes, they call it subtype polymorphism.
Yeah.
So, but then there's the most basic form of polymorphism, ad hoc polymorphism, which is just function overloading. And I couldn't, at the time and for a long time, see that as overloading. As polymorphism, because, well, there's no dynamic binding. So how can that be polymorphism? It's just functions with the same name and different argument lists. But it turns out that, well, like if you look up fold in Wikipedia, they go, oh, fold is a polymorphic function. There's no dynamic binding. It's just got the same name, but it works with different types. How it does it, see, this is, I think, the essence, is that how it does that is not, those are implementation details. From the programmer's standpoint, they go, I understand this concept of fold, and I know that it works with all these different types. And then when I say, oh, I want to fold this thing, the compiler goes, oh, you mean this overloaded version of fold? I'll find that for you. Or when you look at type classes, it's the same thing. You go, I want to do this thing that requires this capability here. And the compiler goes, oh, yeah, there's a class over here that I can invisibly incorporate in order to do that.
Yeah.
And that's another form of polymorphism.
Yeah.
And once you see this, you see it everywhere.
Yeah.
So
your definition again, which I think in your description fits with your definition, was treating a bunch of different things as the same thing.
Yes, more than one type as the same type.
Yeah,
So there, like when you look at union types, that to me is almost the most pure form of it, because you're going, well, I can take a house or a human or a robot, and I can say, okay, you guys are all quote unquote the same type, and then inside the function you have to use a pattern match or some sort of a type check to take them apart.
Yeah.
And back when I was on the C++ committee, I remember Strustrup saying, oh, we don't want people to do type check coding because they should be using dynamic binding for that, which stuck with me. And I thought, okay, this sounds like a really important principle. But when you look at union types, man, that's exactly what we're doing. Yeah. So apparently that idea, ultimately wasn't as useful. I can understand why he would say that.
Yeah.
Like, we went to all the trouble to put dynamic binding in and use it.
Yeah.
But when you look at all these different ways, like um, when you see, like when there's certain types of interface approaches where you say, oh, for this to work polymorphically, I need to explicitly implement all of these types using this interface.
Yeah.
But then there's something called an ad hoc protocol, which we see in, say, Rust and Go and Python. Effectively, it's basically the idea of duck typing, except that it is statically checked. So it says, okay, my protocol has function A and B in it, and I can write my code using that protocol, and you don't have to implement the protocol.
Yeah.
Your objects simply have to conform to that protocol, and you can pass them in.
Yeah.
Versus, oh well, it only works if you have, you implement this base class or base interface. So there's this whole spectrum of ways to do this.
Yeah. What's wild is until, I don't know, a few years ago, I had only thought of polymorphism as inheritance.
Yeah.
And didn't even realize that another form of polymorphism, which I'd used a lot, was actually a form of polymorphism, which is generics or parametric polymorphism. And I hadn't even heard the term generics referred to as parametric polymorphism until, I don't know, a few years ago or something.
Mm-hmm.
And that, I think, started me on the journey of realizing that polymorphism is this much broader concept than what I thought it was. And so I wonder how many programmers out of university are taught that polymorphism is inheritance, and that is all.
Yeah. Well, and I feel like at least that's partially my fault, because the books that I've written that have been used to teach and learn have focused on that, and it's not that it's wrong, it's just that it's too narrow.
Constrained, yeah.
Yeah, it's too narrow. And parametric polymorphism is a great example. I mean, when templates were introduced into C++, that's parametric polymorphism implemented. I mean, it's kind of weird because the template actually creates an overloaded copy for each different type that you give it. So it's like, oh, well, is this ad hoc polymorphism that is just generated by these templates, but the behavior is actually that of parametric polymorphism. Mm-hmm. So it's like, I resisted. I go, well, that's just code generation tools, which are cool, but how can that be polymorphism? Polymorphism requires dynamic binding.
Yeah.
And, once you see it from this bigger picture, it's all over the place. Yeah. So many of these things that we use are, ways to express polymorphism. So
then back to your meta point that you've been exploring for a while is why polymorphism?
Well, yes. I mean, why are we doing it? And that led me to ask, well, kind of, why are we creating functions at all? So this blog post that I put up yesterday, which is, why do we have functions? Why are we doing that at all? And kind of going back and looking at it and the evolution of everything. And it's like, it's easy to make a case for don't repeat yourself. That's the easy way of looking at it. Yeah. But then
so instead of me copying and pasting my script code, let's don't repeat ourselves.
Don't repeat that. Or if you have within your script, if you have things where you go, oh, this code is really doing the same as that. Oh, I shouldn't, just for understandability and maintainability and things like that, I should take that out and put it into a function. Those are the obvious things.
Yeah.
But
remember, we did that last night when we were working on our Gradle boot project. There was a piece of code where we noticed that it wasn't behaving as we expected it to. So we threw it into a function, wrote a test for it. And so just isolating that bit of logic and made it easier for us to test.
Exactly.
Is it working correctly?
So yeah, and there's another factor, right? Which I wasn't even thinking about at the time, but testability. But I think ultimately, because there are functions that you might only call once, but you want them to be partitioned for testability, and because I think it's a concept. So I think what it ultimately comes down to is, how do you partition your program into concepts? And if we think of a function as a concept, then it's easier for the programmer to understand, ideally, if you choose the right concept partitioning. But there's testability, there's reusability. If you've come up with a good concept, like fold in functional programming is kind of a well, all the things that get rid of looping constructs, those are concepts. But then if you look at, okay, why are we doing polymorphism, that hopefully will just say, oh, well, I have the same concept and it makes sense to apply it to multiple types. And I think ultimately it's all about making sense to the programmer and testability. Now that you've said testability, it's just like, oh, how was I not thinking about that?
Yeah.
And ideally reusability, but that's not always the case. Sometimes you say, I want to print something. The print function has a way to accept different types of arguments and do its job.
Yeah.
So the concept of print, we all get.
Yeah.
Or read or whatever. So
well, it's interesting that we generally name functions, and so what we're doing is we're ascribing a name to the concept. There are places where we don't, where we just use anonymous functions, and I think most of the time when we do that, the concept is more about a transform, and the name is kind of irrelevant. Like, because you would, let's say you want to, in a map function, you want to convert foos to bars. You could make a named function called foo to bar and put it in your map function call. But the name is kind of irrelevant because you've got the input parameters and the output. And so you're doing a transform from one thing to another thing. So the name isn't as important. But I think, I like your framing of, a function is a way to express a concept. And sometimes we subscribe names to them.
When you use a lambda, generally that's a short thing. And so when you're reading that code, you can go, oh, I'm mapping. So I'm transforming from one type to another. Here's the transform, and I can see in this short thing what's going on. And so naming it is kind of superfluous. Python goes to the, I don't know how much of this was thought out explicitly and decided this way, but with Python you can only have a single expression in a lambda. It's kind of an awkward syntax. But you can't, so if it's any more complicated than that, you basically have to create a named function.
Not a terrible design.
No, it isn't. Other than decision. You actually have to say lambda colon arguments.
I forget the syntax. Is a little awkward,
people don't use it that much, so it's and
interesting to say that it can't be more than a single expression to be anonymous, essentially.
Right.
If it's more than a single expression, give it a name.
But from this standpoint, you go, okay, that actually sounds like a considered design decision, because if it's more complicated than that, it's going to be hard to read.
Yeah.
And most of the time when you're doing, maps and folds and things like that, you're probably going to want it to be fairly concise. Otherwise it immediately gets too complicated. It's that scaling thing.
A lot of those cases where you use those anonymous functions, the name would be obvious. It's
Right.
And foo to bar, and it's like I don't really need the name because I
Yeah.
can see it takes a foo and returns a bar.
And it's more important, what am I doing in
Right.
that provides meaning,
Yeah.
and giving it a name is,
Yeah.
yeah, I mean, it's, you look at the function, then you have to go, okay, what's the function doing? You have to go look at the code to
Yeah.
have it make sense to you. So small, every once in a while we run into this thing where we go, oh, here's a thing that doesn't scale.
Yeah.
So lambda's getting really big in a situation like this. No, that doesn't scale.
Yeah.
And it's pretty obvious why it doesn't scale.
Yeah. There's another category of this which is interesting, is on the naming topic. There some people like to have operators. Some languages allow kind of any operators to be defined, and I like to have names for things like that. But there are some people who are okay with not naming certain operators, and instead relying on just the visual appearance of the operator being the way to explain the concept. So an example, a slightly deviated example of this is in Scala, the fold operators are supposed to visually represent like dominoes falling, and so
The folding left,
the folding left,
right.
and the slash represents which way the fold is going, and that one does have corresponding names, so it's not the exact correlated example, but is interesting that you could use ASCII art essentially to visually represent the concept of what a function is doing as well.
Yes, and that relies on the programmer of that to be to have a sense of what's going to appeal, what's going to make sense to everybody. And I think the experiment that Scala did, I would call it a great experiment because it showed us what not to do. And whereas, see, look at what Kotlin did. Kotlin followed the Python model, which is, if you want to overload an operator, you overload a word. I mean, you define that word.
There has to be a name.
That's the core definition.
Yeah.
And also, there is a limited set of operators that you can overload.
Yeah.
So you can always call the function name if it is confusing to use the operator.
Yeah.
And it's always there. And it's like, okay, that was the way to do it. And
my proposal to Martin long ago was that there should be a requirement that all operators have to have a ASCII name associated with them.
Right.
And I think at one point he experimented with that idea, but don't know where that went. But yeah, I don't know if I would agree that you shouldn't be able to create your own operators. There should maybe be some constraints around it, but I do think that every operator should have a name.
At the very minimum, you should be able to call the name and or look. Well, I think that's the thing, the searchability of it. You should be able to look up the name.
Yeah.
And go, what the heck is this thing doing?
I think Haskell has this whole website where you can search the operators. So they've created their own search engine for the operators.
You shouldn't have to do
that. Right.
Yeah. Well,
seems like it's indicating that.
Right. And even operator overloading in C++.
The point where you're inventing a search engine to solve a problem, you've maybe taken a mistake.
Yeah, if we had already had something like IntelliJ, then it would, because you could always go, what's this operator do? Yeah. Click, and it takes you to it.
Yeah.
But ideally you shouldn't have to do that. So I think, it's been I feel like the great benefit of Scala has been pushing. Well, one of the great benefits has been pushing us forward in, let's do this experiment and that experiment, see what happens. And sometimes what happens is not great, but now we know that. Now we know, let's not do that.
You don't like the tilde dash pound greater than operator with no name?
I don't even know what that is.
I don't know. Yeah. There's some wacky operators for sure.
Yeah.
Okay, so hopping back to polymorphism real quick, I was thinking about extension functions. Where do extension functions fit into this worldview of polymorphism?
That, that's a that one isn't clear to me because my initial experience with extension functions, which was in Kotlin, and it was like, oh, this is just some syntactic. Sure, it's like you've got a type, and you can add a new function, a new member function to that type, as long as it doesn't try and you can't touch any of the private stuff. So you're not violating
The
the
rules of, yeah.
encapsulation of it. You can add this new extension function, and it's just like so it's just this little syntactic convenience. But then when you have some other function that takes that type, that function now is able to call the extension.
Yeah.
And that's when you start going, wait a minute, there's more going on here than meets the eye. Because if I want to write a function that does extra things to this type, I can add an extension, and now I can do the extra things in my. What is that? Is that polymorphism? I don't think so, because it's really about extending the capabilities of a type.
Huh.
But I suppose you could also say, what if I have a union of types, and it's almost like it's duck typing,
Hmm.
because you're saying, okay, I'm going to assume that this function exists for this thing, but you have to make it up, which now it seems like we've come back to type classes.
Yeah.
You know,
Yeah.
well, and the thing that doesn't freak me out about this now is that I'm looking at all this stuff as variations of polymorphism.
Right.
And so you're going, okay, maybe this is a variation of polymorphism. What are we what are we trying to achieve here?
Yeah.
What is it that we're trying to do? And extension functions are a lot more, you know, I, that there's a mystery in there that I haven't figured out. And it's like, it seems so simple, and yet what you can do with it now is more.
Huh.
And so, yeah, what is the mental model for extension functions? Um,
Yeah, I
I
mean, I
don't
guess
know.
in some ways, an extension function is really just giving you a nicer experience than the alternative, which is just having a function somewhere
That
that
takes the thing
that
as an
takes the
argument.
thing as an argument, right?
Mm-hmm.
So that's the way that we would normally do this without extension functions. But being able to dot complete on a thing and see what the available extension functions are gives you just a discoverability that wasn't there. But I guess
That's
like,
cool. That's really nice. But I think this idea of, okay, this type that I'm passing into my other function now has more capabilities that I can call within this new function. That, I think, is the real
hmm,
twist. Because that's when you start seeing kind of surprising things. And and then being able to say, oh, okay, what if I do it with polymorphism, and all of these things somehow have that capability? Maybe some of them are already built in, that operation. So it gets a little closer
yeah,
to duck typing, structural typing,
yeah,
but it feels different than any of those things.
yeah.
So
What's weird is how sometimes these different strategies for polymorphism intertwine, because a while back you and I were playing with type classes, and we realized there's kind of this like combination of extension functions, parametric polymorphism, and type classes that like all comes together to be useful.
mm-hmm.
And so it's weird how you've got these individual strategies, and sometimes we assemble them together to actually be useful.
Yeah, although from a readability standpoint, that could produce some really obtuse code. Well, I mean, for example, some of the code in the Red Book, the
Yeah,
functional programming in Scala book,
yeah,
it can be that way.
Isn't in Rust, type classes are built on top of extension functions or something like that, right? Like the way
Well,
that
so
you
in
use
Rust and
them.
Go, and this is really, I mean, there's a number of really interesting things there. And one is, it is not the idea of reusing code through inheritance is removed. So all you have is interface and implementation, and you don't inherit from implementation. So there, you could sort of see the philosophy here is that reusing code through inheritance is a bad idea. In Smalltalk, sure, it worked, but Smalltalk was a completely different beast, very different from Java. Java was, and it was saying, oh, we'll be like Smalltalk, everything will be an object, you reuse code through inheritance, et cetera, et cetera. But Java is a statically typed language. Oh, that doesn't matter. It does matter. Smalltalk is inherently dynamic. And so that really changes the picture. And you don't just get Smalltalk when you turn that into a statically typed language.
Yeah.
You have to have the Liskov substitution principle. You have to have, all of these constraints, which make it, no, it's not like Smalltalk. But so this idea of reusing code through inheritance in uh, Rust and Go, and I think some other languages, the language designers said, we think that's a bad idea. If you want to reuse code, use composition,
Yeah.
which is all that is happening anyway. When you're using inheritance to reuse code, the compiler sticks an object into your new object. And I remember learning this way back in the C++ days, and I go, I didn't get it. I didn't really see it. So they're saying, if you want to do it that way, do it explicitly. And then you have to say, oh, my embedded object dot operation that I'm performing on. And when you read that code, it's clear. Whereas without that, when you're doing it in inheritance, you just call the function. And it's like it goes to the base class somehow, magically.
Yeah.
So it's like, I think there's this general movement to not having multiple levels of inheritance in order to reuse code. And I mean, how often have you actually done that? Anyway, reuse code through inheritance. I have an example that I made up while I was thinking of this, and I go, oh, okay, I can see it, but still,
likely there's a better way given a different tool set.
Well, even in my example, it's only a single level.
Yeah.
And so it's like, okay,
just use a sum type.
you could do that, right? So the way they do things in Rust and Go is they say, okay, we have the data structure, pure data structure, not necessarily immutable, but the data structure and the operations on it are only associated through extension functions effectively. I don't think they necessarily call them that in that, but I'm not sure. So you do that, and then so basically it's all extension functions, and there isn't even an opportunity to it's not
define
really
base logic.
Yes. Yeah. Well, I mean, they do have the idea of an interface, but that's kind of it. So it's I think the resulting code from that is going to be a lot cleaner because you don't have all these choices. Yeah, which we do in these other languages.
Yeah, and I think there's some difference between what an application developer needs and what a framework developer needs. It does seem like there are cases where in frameworks inheritance is more useful, but I don't know. Well, I have not really used inheritance beyond some types in product, like
basic usage. Which these languages are saying, that's what it's for. And when Luciano Ramallo was here, I mean, he was here for a week, and that came up because I was working on this. And his opinion is that inheritance is for frameworks. And or even just the interface implementation thing. And you think about that and you go, all right, if we change our perspective on what a framework is, because we usually, it's a web framework or machine learning framework or something, these big things that are giant architectural decisions. But if we change it and say, well, a function can be a framework if the intent of the function is to allow more types to be worked with later. If it wants to expand the number of types it works with. So that's a very small version of a framework. But then you start going, oh, well, all right. So if I want to be able to use more types, then that's a quote unquote framework function. And that's where I need polymorphism. And that may answer the question of design. How do you design? Well, A, how do you decide what a function is at all? And B, if you've found a good concept, maybe it should be polymorphic. And if it's polymorphic, okay, then you've written a function that represents a little mini framework here. Because even within your program, you want to be able to expand it. So you go, oh yeah, later I might want to add a new type of pet or shape or something. So I'll have the functions that work with it be little kind of mini frameworks. And then it's easier to extend your code, to expand it, to develop it. So I guess it's sort of an architectural decision. Even in the small.
Interesting to go back to some of the language designers we've talked to, or specifically around more newly created languages, and ask them what their approach to polymorphism is. Because I have a hunch that if I was designing a programming language today, I don't think I would have inheritance. I think I would have ADTs, sometimes product types, and I'd have type classes. And that may be sufficient.
Yeah, I don't know.
And parametric polymorphism, of course.
Yeah, I don't know. I mean, some form of protocol. It turns out there's a spectrum. There's, if you have an interface that has to be implemented by the types, then it's sort of an upfront decision, you could say. And then if you have an ad hoc protocol which says, yeah, as long as you conform to this, I don't know.
I think type classes can do that, but maybe you need inheritance for type classes.
Well, and I guess we should probably distinguish between inheritance versus implementing an interface. Yeah. So
I think that, well, let's see. Can some types always? Yeah, maybe some types, because they don't allow some arbitrary person to extend the base.
Right, because they're sealed. Whereas type union, you can work with completely disjoint types that have nothing in common if you want. Which is that's the thing. It's like, okay, say it.
It depends.
Yes, exactly. It depends on what problem you're trying to solve, and then you look at these and you go, oh, this is just a selection of tools. And I, as the program designer, has to understand them well enough to know, oh yeah, this is a better use, or this will be an easier use. I don't know.
Things were easier when the only tool in my toolbox was inheritance. Then things were easier.
I wonder about that, because there was this whole movement to actually there's this big fight over how do we design objects. I mean, seriously, there were people who were getting up at conferences and doing battle with each other. It didn't devolve to fisticuffs, but they were going, yeah, we got to represent objects with boxes, no clouds. Literally, this was the level to which the battle had devolved. And in the end, I don't think any of these really helped figure out how do you decide what an object is. I mean, maybe domain-driven design probably was more useful in that case than anything else, but it was like, and in the end, I didn't come away going, I see now, this is obvious. And I think it's just, this is where it becomes more art than science. And because ultimately, so the conclusion that I came to was the concepts were to communicate to other programmers, not to divide it up into units that could be partitioned to programmers by managers. It was the concepts so that other programmers can come along and read your code and understand it. Code is read more. It's not that it's read more than it's written. It's more that somebody has to understand and maintain your code and try and reuse it and all of these things. And so you're communicating to the other programmers and to new programmers.
Yeah.
And that's ultimately what is going to create a good system.
Yeah.
And the thing that the structured analysis and design was really trying to solve was we need programs to be written faster. They need to be bigger and more complex. And the old techniques that we used were for relatively small scale programs, where you could throw, even in the case of sending a rocket to the moon, which was all assembly language, you had to get it right. You had to throw tons of programmers at them. It was way expensive. And it still, by today's standards, was not that much code. And so we needed programs faster. And so the compromise was, all right, we'll figure out how to make programs faster. They'll not be very good programs, but the need is more programs.
Yeah.
And so, which was a rabbit hole that was probably, we're trying to back ourselves out of now.
Yeah.
We're trying to go, okay, turns out reliability is important. Program created quickly that doesn't work very well is not actually what we need.
Yeah.
Or
I do think that part of what happened in this journey was that the way that we decided as an industry to encapsulate things into functions or objects ultimately was not very easily shareable to other people because of mutability and side effects. And so
even if you are encapsulating this code and only the methods in the object are able to manipulate that, it's like, okay, well, I know only these methods are mutating my state, but it was a step in the right direction, but it didn't really, it still could get super messy and hard to track down.
Yeah. So I think that now with the functional programming becoming more predominant in OO languages, we now are actually beginning to see that dream of partitioning with functions, partitioning work across multiple humans, become more of a reality. But we first had to figure out that mutability makes this really hard and side effects makes this really hard.
You're saying that as if we've already figured it out, but go ahead.
I have, but
it works for me.
Yeah. No, I think there are people who in our industry who have really figured this out.
Absolutely.
And are at this forefront of a much more productive way of collaborating with teams and many people, because we've finally figured out, if we do this with these boundaries, then we can actually make that dream a reality of sharing functions and not having to worry about, was it thread safe? What was it? What effect was it?
How did the state get wrong?
Yeah.
Well, and look at objects in another way. It's like, okay, we solved this, quote unquote, solved this problem by using encapsulation, but now everything that manipulates that object has to be inside of that class. And there's going to be duplicated code all over the place because I create a new class, and you're going, oh, well, that's what code reuse through inheritance is. But it's like, man, that hasn't really. I mean, we're still doing the same thing in all of these different types that we're creating, and so we didn't. And ironically, that was one of the things that object-oriented programming was supposed to help was eliminating code duplication, but I think ultimately it forces you to duplicate a lot of code.
Yeah.
And for there's certain things that you need to do for every object, and there's certain things that turned out to be common among maybe even just your set of types. And so whereas when you can say, okay, we just have this naked structure that's immutable, then we have this set of general, we'll call them high-level primitives that we can apply to this thing, and now we're not duplicating all that code.
Yeah.
So this is why one of my perspectives on functional programming is that it's, radical, not repeating yourself.
Yeah.
Radical reuse of code, which, but that doesn't define functional programming. That's just one of the things that we get from it.
Yes. Would agree with that.
Mm-hmm. Yeah. And now the thing that is left unanswered is the design question. Is like, okay, if we do see what functions and polymorphic functions and things are, how do you design with them? And I think with all of our struggles over the years, nobody's really been able to approach it. Maybe it's just not a formulaic thing.
Yeah.
I mean, there's the math approach, which we were talking about this morning. It's like, oh yeah, we start with category theory and we can legitimize all of these high-level primitives that we've discovered in functional programming over the years, the maps and the folds and the filters and stuff. Yeah. And it's like, cool. But from the average programmer's standpoint, they just need to know, they just really want to see the toolbox.
Right.
And if you start mathematically deriving it for them, they're just going to go, oh, functional programming is too hard for me.
Yeah.
You don't want to do that. That's been tried many times and it hasn't worked. I think, I think even using the term monad at this point it just drives a lot of people away.
Yeah. It's not helpful.
Let me explain category theory to you and it'll make sense. And it's like, nope.
Josie, my almost 7-year-old, she's been learning math and enjoying it.
You've been teaching her category theory?
Yeah, that's where we started. Was category theory.
Well,
I'm like, let's not use addition. Let's not jump so far ahead.
Yeah.
Let's first learn category theory before. Mm-hmm. No, of course not. Like, she's learning addition and multiplication, subtraction, all that stuff. And at some point she's going to learn, oh, there's some theory and laws underneath all this. And that I don't think you could, it would be so useless to try to go the other way.
Well, you would have to rethink it on such a, you probably could, but the rethinking of it is so, you have to go, okay, these blocks, you can switch them around and they're still the same blocks somehow. I don't know. You'd have to come up with such a basic and clear and related to the world way of doing things. But, when you took algebra, they basically, ideally, they started by saying, oh, look, if you do this and this, it's the same. And so you can, that's what I mostly remember from algebra is like, it's a set of mechanical things that I can do.
Mm-hmm.
And I didn't go to I didn't internalize the proofs that showed why you could do this. Those just went, proofs never worked for me. And
I'm glad they're there.
Yeah, you're glad they're there. But then I didn't really internalize algebra until taking calculus and more advanced things, because then you were just using it all the time.
Yeah.
And so I really think that.
Does this relate to philosophy, like the forms? Was it Plato's cave, and we experienced the world, and
in an indirect way.
Yeah, and we. It's hard for us to really grasp the abstract things underneath or something.
We see the images on the cave wall, and we have to infer the quote unquote underlying reality.
Yeah.
That that's kind of what he was saying. We don't have direct connection to the underlying reality.
Yeah.
Yeah. And so, but I think a lot of the problem with what people have tried to do with functional programming is the ones who get the underlying theory and it's just so amazing and beautiful to them, they go, oh, I have to get this to you because this will form such an emotional connection between us if we both get it. And they don't really understand that for the vast majority of people, their entry point needs to be, I'm trying to do something. How does this solve my problem? Why should I? Well, this podcast that I heard, the fellow who was talking about how recursion is just kind of a silly thing. It's like, how do you get you? You need to ask the question. And it's like, well, what problem are we solving here? And the underlying problem is actually kind of subtle and mostly not what people encounter in their day-to-day, let's say, scripting experiences.
Yeah.
And it's like, from that standpoint, recursion is something that, you don't use it on a day-to-day basis at all.
Yeah.
But
I'm glad it's there.
Well, and it is an important foundation of some of these high-level primitives in functional programming, for example, or there's certain types of problems that it comes up. But
So back to Plato's cave.
Yes.
So the way that we generally try to explain functional programming is someone is seeing the shadow on the wall, and we say, now close your eyes. Let's talk about the thing that is casting that shadow.
Right.
Right. And which is just totally useless. Like,
unless you're a philosopher,
right,
and you're curious about that kind of thing. But to go, oh no, but you have to understand the thing that's casting the shadow, or else it won't. You won't believe that all of this stuff works. But most people are coming from the standpoint of like, I see it, I believe it,
right,
and whatever's underneath it that's abstract.
Yeah. All right. Well, I think my brain is full.
Okay.
That was fun, and look forward to watching your Strangely recording when it's out.
Cool.
And reading your blog on functions.
Yeah.
What are they good for? Right? Is that what it's called?
Something like that.
What's your blog?
It's called Why Are There Functions?
No, what's the domain?
Oh, it's bruceeckle.com.
Okay, on bruceckle.com.
Yeah.
Cool.
All right.
Thank you.
Sure.